In this lesson, we're going to look at how the energy gets stored in the magnetic field of the inductor as the current begins to flow through the solenoid and the B field begins to grow. So we're going to begin our analysis by flipping the switch to position A and letting the current flow. So the battery is going to start to push current through this circuit. The current is going to flow down through the solenoid. It's going to make a magnetic field in the core of the solenoid. So as this magnetic field begins to grow, we'll see that that will correspond to the energy of the solenoid increasing. Well, our analysis starts with a conservation of energy statement through the Kirchhoff loop. So we have the Kirchhoff voltage loop of our current that we just indicated, so it's that outer perimeter loop that we're looking at. Sum of the voltage sources equals sum of the voltage drops. We have the battery voltage pushing the current. We have the back voltage from the inductor, the negative L di dt, and we have the voltage drop across the resistor. Well, all we're going to do algebraically is to bring the negative L di dt over to the other side to get our positive here, but it's not really the equality we're interested in so much in this analysis, but it's the individual terms. And as it says here in my exploded statement, because I always remember this analysis as really boiling down to the trick, is nothing more than to see that we are going to multiply I through this entire equality. So the conservation of energy statement now becomes a power statement because we have IV is the power or the rate at which the battery is doing work. We have I squared R, so it's nice to see that our terms, our equations are being consistent for us. So we've seen these before. Power dissipated by the resistor. And now we also realize an Li di dt term. So that term, since IV is power, I squared R is power, this must also be a power term. So it is, and it's the power term that describes the rate at which the energy is being stored in the inductor. So we're going to focus on just that L di dt term for a second and realize that it's the joules per second of energy being stored in that L, that inductor. And the best way, I think, to see how that equation plays out is to put in some numbers. So I have here a simple example, simple numbers. I have an inductor, a 2 Henry inductor. Let's assume in this example that the current is flowing into the inductor given by I equals 3t squared. And we are being asked to find the power, the instantaneous power, energy per second, as the magnetic field begins to build in the inductor. Well, we need the I term, so we need t equals 1 second. We get 3 times 1 squared, so we get our 3 amps. Di dt, now we have to take the derivative, so 3t squared is 6t. Plug in 1 second, 6 amps, and now amps per second. And now we have all of the terms that we need. So we have our L, 2 Henrys, our current, 3 amps, and our rate of change of current, 6 amps per second. So we get 36 watts of power being delivered to the solenoid, to the B field of the solenoid at t equals 1 second. Well, to go from our power expression to an energy expression, we are simply going to integrate both sides, so please make sure you get this down into your notes. So our integral expression is nothing more than our power expression, where we're going to cancel out the dt's, so the time differential. Now when we integrate both sides, the integral of du is u. L is a constant, so it comes out of the integral. The integral of I di is I squared on 2, and voila, we have our energy expression. So as it says here, this is the joules of energy stored in the inductor for any given I. Well, we now can just perform some very simple algebra. I'll leave the whole page here for you to pause and take a look if you want to pause, but we have some very simple algebra to look at to get an energy density expression. So what do we mean by an energy density expression? Energy density, by definition, so the energy per volume stored in the magnetic field is stored in the magnetic field of the solenoid, right? So the volume of the solenoid is the cross-sectional area times the length of the solenoid. The energy in the solenoid at any instant in time for a given current we just calculated was 1/2 Li squared, so we would substitute that in here and get our expression down here. Just algebraic. So we're going to also use our result for the inductance value for the solenoid as mu naught script n squared L on A. We're going to substitute that term in for L. So take this and substitute it in for L, and that's all we've done down here. And now look at what we get. We get some very nice cancellation. The L's cancel out. The A's cancel out. And we are left with 1/2 mu naught script n squared I squared, and we know the B field inside of a solenoid. So we're really just using all of our equations and some easy algebra to manipulate our variables. So script n I squared is going to be B squared. We're just going to square each and every one of these terms. So script n squared I squared is B squared over mu naught squared. So we're going to plug that in for the script n squared I squared, and we get our energy density expression for the inductor. So this is the energy per volume, right? So this will be the joules per meter cubed inside the core of the solenoid. Now you will not have to do the derivations, so these are equations that I want you, when you use them, to recognize them as coming from a logic, a structure, both mathematically and conceptually, that makes sense, so that when we're going to use them in the future, and a quick look ahead, and next page of notes is just a chart but no annotations, is to look ahead to our next chapter. Our next unit will be looking more at how capacitance and inductance interact together in one circuit. We'll be looking at what is called LC circuits. And then finally, we'll see how Maxwell took a lot of what is going on here and the similarities we see in the structure of the mathematics, and it gave us a formalized theory of electricity and magnetism. So a lot going on actually in these equations to unpack, but we will be doing that in our next couple of chapters.